So, okay, a very good afternoon. So I almost forget today we have a lecture, right? Too much holiday, too much holidays, and then yeah, that's why then I see I forget to always I forget to create the link right in this Microsoft Team. So no worry. Once I open my Microsoft Team, how come no one's create means that no one joined my the today lecture, then I only found out that I forget to make the Microsoft team link for today live lecture. So too much holidays for this for these few days. So anyhow, we're going to meet physical next week, right? Yeah, physical next week. So today we will touch on more on the theory part about these coin integrations. So I would like to share my screen here. Yeah. So so about the attendance, no worry about that. So I will take notes in the spectrum later. So now, today we're going to touch on this coin integration and the error correction models. So in the last week lectures, we discussed about this, what we said, the unit test, right? Unit test, and then the idea behind the spurious regression. So idea behind spurious regression, then actually what motivates us to proceed to this to test for the coin integration. Because if we have a spurious regression, then if you use the normal OS or the least square method, it will create spurious regression. Am I right? If we combine what we say the I1 variables, if the variable is integrated of order ones, then if we use the conventional approach, for example, the OS approach, to estimate such equation, the variables in one equation, then we will create the spurious regression. That's why the idea behind the coin integrations pop up, right? Due to this spurious regression. Then that's why last week we also introduced you the several tests, for example, the unit test as well as the stationary test to what we say to check whether the series is it integrated of order one or integrated of order zero. So it's very seldom uh, the series is integrated at order two because if we first difference the variables, normally the series will return to their what we say to their means, and then the variance are constant. If we still not stationary at first difference, then your second difference the series, then we have to use the appropriate approach to handle the I2 series. Yeah, that is another approach. So we introduce you the unit test, right? For example, the IDF test, Phillips parents, and then the KPSS. Actually, we have one more test that is not normally applied in the research. It's called Earth and Parent, which introduced in 2001. Right, there are several unit tests that use the what we say in this research. And when you go through the journal articles, that's the conventional unit test. Then, as you say, actually, can we just apply one unit test? Normally we will apply three, uh, three, like a normal apply in the previous research three, because for us to what we say to come up with the um, one conclusion, right? For example, the unit test actually stationary. Like what we applied in the last week lecture, right? Unit test actually is I1 based on the ADF, but it's an I not based on KPSS, for example. So we need to have something like the more dynamic, right? More dimension to test our series. So not only unit test, stationary test, we also discuss about the causality, right? Because it's a regression, right? Regression, which we're going to introduce you later. Actually, it's different with the causation and also the correlation. They are totally different because um, regression actually does not means it means if we have a significant, for example, the variable x1 on the y, not necessarily imply that there is a causation from x1 to the y. So regression does not imply the causation. And also, if there is a high correlation, not necessarily the series will have the significant impact on the x to the y, for example, right? So they are totally three different things. So today we are going to talk about this co-integration. So the idea behind co-integration, and also introduce you the error correction model as well. So what we're going to cover today is the details is about this short run and long run relationship. Okay, so the short run and long run. So we will introduce you the test, Johansson co-integration test. And then next week, we're going to touch on this, the approach that allow us to handle the I1, I0 series, which is called AIDL approach. For those that already took, for example, took the financial econometric in the last semester, perhaps they have some idea behind the AIDL approach, right? So next week, we're going to discuss about the AIDL approach and calculate their respective multiplier, right? So today we're going to discuss a bit the short run and long relationship and co-integration test, as well as the estimation and testing. So if you go through my spectrum, I also uploaded the serverless like the YouTube, right, to get you how to from the VCM, from the WA, and then their respective granular consolidated as well, right? So as continue from our previous discussion about these vector autoregressive models, the WA, right? So still, do you still can recall the time series approach that I discussed in the last week in the first few lecture, in the first few slides? So if we have found out that there is a co-integration, then we have to proceed to the VCM, right, to allow the error correction to take into account to convert back into the long run. Now, how about this WA, the vectors, right? The vector autoregressive models is WA, which if we, for example, if we do not have something like the co-integration, then we can estimate the, it means that estimate the variables within the within this vector autoregressive model. It's different compared to the what we introduced you in our financial econometric, which we call as a value at risk, right? That's totally different thing. There is a aberration for the value at risk, but now we are talking about the one of the econometric approach, which is called vector autoregressive models. That's why we in the aberration called VAR. So as you observe from my slide here, so I have a y, right? I have a y as my dependent variables. I also have a zt as my dependent variable. Can you still recall the granular causality that we discussed in the second half of my lecture last week? So the actually y, right, is a vector, so it's allowed the, when we say allowed the dependent system to become, means that the variable system become means that the variable appear on your left will appear on your right now. So it means that it's a vector. So all the variables, which I can say all the variables can become your dependent variables now. So that is the dynamic. I mean that is unit of the WA. It's no longer single equation. Yes, it's a single equation. For example, here I can say YT. Then my independent variable consists of YT minus 1 up to YT minus P. And the P here actually is a length. It's a length. If we subscript T, it's a time series, right? Subscript T, then T minus 1 means refer to the lag for the YT. It's a lag 1 period. For example, T here is year 90, right? 90. Then the T minus 1 will be year 89, right? And then up to T minus P. Depends on how many lag behind, how many lags, right? Then how about the Z? Z refer to the addition, for example, the independent variables, right? Independent variables, and then on the left, T minus 1 up to T minus P as well. So this is a single equation. If we allow the Z mean become my dependent variables here, then will become the another additional, means that another equation, right, will appear in the vector form. So ZT, then and then followed by my YT, right? But the YT here is YT minus 1, right? It's a lag because the WA models, right, is a collection of the vector of the time series on upon their own past value, and also the past value of the other series as well. So which refer, for example, if the equation is ZT, so not only on past value, also by the past value for the other series as well. So there's a meaning single equation, right, for the zt. Then the yt is not only by its own lag value, also by the others past value, right, for the zt variables. So can you just have a two? Not necessary, right? We can have a more than two, right? For example, if I have a j, for example, have a j series. So I've also including another jt minus 1 up to jt minus p in my first equation, and also in my second equation. And then in my third equation will be my jt as a function for the yt minus 1 up to yt minus p, then zt minus 1 up to zt minus p, as well as the jt minus 1 up to jt minus p as well, right? So they have a three, right? Three vectors. It means that three equation in one vectors. Then still remember or not, in our last week lecture, I used this the money supply, right, and the GDP, right, and then test whether the past value is it going to affect another variables. So here actually we can use the F test, or we call it as a war test, to see whether the past value of the series have to predict the value for another. For example, I want to see whether the zt in this equation going to affect the yt or not, right? So I can use the F test. So that is that's how the vector autoregressive works. So so the important point here is the y is a system, right, of the equation is a function of own lag, and also the lag of other variable in the system. So how about the VCM? The VCM is called as a vector error correction models. It's a vector error correction models. So it's a special form of the VALA for the I1 variables. So why? Because if the variable is I1, but there are no configuration, then we have to first difference the series before we estimate the variables in the VAR form. So if there is a what we say, if there is a no configuration, but the series is I1, right? Because I1 already, so we test for whether there's a configuration in the long run or not. If there's a no configuration, then we proceed to the VAR, right? So in the VAR form, then we have to first difference all the series because they are I1, right? So we have to first difference the series before we estimate, before we test whether the Z is going to affect the Y or not in the VAR. But if the series is I1 and also configured in the long run, then we have to use the VCM. So it's for those variables that are configured, not only I1, but also configured, then VCM. Okay, so there is a difference between Y and VCM. So additional note for my gradual causality test, right? So we can actually we can test for the short run and long run causality. So if you go through my what we said video, right? Video I uploaded in the Spectrum. Actually, we can test for whether we have a short run causality as well as whether we have a long run causality. So okay, is it interesting, right? Whether is it a causality appear only in the long run or appear in the short run? Is it only short run venture from the money to the income, or long run from the money to the income? So we can know the implication now, right? And so it depends on the if this requires the use of error correction models, right? Actually depends on whether there's a configured or not. Actually, what we introduced you in the last week is the series actually is I1, right? I1, then we apply just a normal configuration, a normal gradual causality because we did not touch on the configuration yet. Today we touch on configuration. So if the I1, then if the configured, then we need to use the VCM. And this VCM we can also test for the causality as well. Okay. And this long run causality is determined by the error correction term. We can use this ECT. What we're going to talk more about is ECT, which is called error correction term, to test for the long run causality. It's just based on the ECT, whether it is significant or not significant, to see whether the x to the y or y to the x based on the ECT in the long based on this long run to test for the long run causality. Then how about the short run? You just test the lags independence variables. So just like this one is for the short run, right? You just want to use the war test or the F test to see whether the lag independent variables whether significant or not significant in the particular equation. That's based on the short. That's the one to test for the short run causality. So there's a difference. Short run causality, just like what we discussed in the last week, as well as just now, to see whether the Z going to affect the, it means, is it the F test? Is it the F test in this first equation, whether significant on the Y or not? So that is significant of the F test, or we call it a wall test. So that's used to test for the short run. Then the long run, we used to test for the based on the ECT, the error correction term. That's for long run causality. Okay. So before the error correction model can be formed, right? So you have to test whether we have a cointegration or not, whether we have evidence of cointegration. If the series, right? If the Y series and X series actually they are I1, if they are I1, right? So we have to test whether there is a cointegration or not, right? Cointegration or not. So if there's a cointegration, then we have to proceed to the error correction models, right? Error correction model to see, to check that if there is a cointegration, yes, then we proceed to the error correction model. If there is no cointegration, then we just use the normal VAR, right? Normal VAR. So if in the vector form, so we call it as a VECM, the system form we call it as a VECM. So in this long run, as I mentioned just now, is based on the significance of the ECT. So to see view as an indirect test of the long run causality, right? This is an important point for you to bear in mind that if let's say ask you to test for long run causality, it's based on the ECT. Okay? So is it possible to have a long run causality but no short run? Yeah, it's possible. There's a statement here, right? It's not a question mark. So yeah, is it possible that there's a no long run causality? It means that if based on the F test or the wall test, to do the restriction on the independent variables or the explanatory variable, actually not significant. Not significant, right? So there's a no short run causality, but the ECT is significant. So is it possible? So that's why you can say wall test not significant, but ECT significant. So it's possible to have a long run, but no short run. Yeah, that's the meaning. So but in the multivariate causality, because what it means a multivariate, more than two variables. Like last week, right, we introduced you just two, right? The GDP and also the money only, just two, right? So how about if I include one more interest rate? So is it a little bit difficult, right? It's a little bit difficult to test for the long run. Why? Test for the short run is okay, no problem, because you just do the restriction test on the respective leg, right? T-1 up to T-P, I write it in a simple way. And then just the interest rate from the T-1 up to T-P. So therefore, this for the first equation and then for the respective equation as well. I just need to, if I want to test whether M greater cost of Y, I just need to do the restriction on this leg only, right? To test for the short run. But for the long run, because if let's say all my series actually is I1, all my series are I1, then I test for cointegration. If I found there is a cointegration, then I proceed to the VECM. With this VECM, I can test for the long run causality, whether there is a long run causal from the M to the Y or not. But it will have a probabilistic, as mentioned here, for this multivariate, because the ECT here, the error correction term here, is represent not only the M and also the IR, right, to convert, to go back to the long run equilibrium. So there is a little bit problem, challenging, because it's more problematic, because it's impossible or to tell which independent variable is causing the causality through the error correction term. So there is a little bit challenges for us to based on the ECT. If we have more than two in the what we say more than three variables for the multivariate case, more than three variables. But for the bivariate is okay. Like the exercise last week is okay. Just Y and M is okay. For us to test whether there's a long run for the M to the Y or for the Y to the M. but not include the interest rate for this multivariate case. Okay, because the ECT here consists of M and IR. If this ECT is significant, so is it M going the long run gradual cost of Y or the IR long run gradual cost of Y? It's a little bit blur, right? That's why it's a little bit problematic here. So normally for this multivariate case, we do not use this ECT to test for the long run causality. Okay. So this is just a slide how the VCN model look like. So as a similar like if there is I1 series for the Y, Z, and X, so will be first different for all the series, okay? Then we'll include one more ECT term here, T minus 1. The error correction term T minus 1 in the first equation, and the error correction term T minus 1 in the second equation. Right. So this one will involve multivariate, right? Because we not only have a Y, we also have a Z as well as the X, right? As well as X, which is three-variate, is a multivariate. So that's why the ECT here just indicates there is an error correction adjustment in the long run to go back to the equilibrium. But we cannot use this one to test for the long run causality. Only test for the short run. We can do the restriction based on the, for example, whether the ZT going to affect the YT. We can do the restriction based on the beta 4 and beta 5. Right? These two whether equals to 0 or not equals to 0 in the first equation. So now, that is the general idea behind this VCN and the VAR. So now about this conjugation method, right? So H3 is leading, means that it's normally people use in the macroeconomy, right? So because H3 is used to model the equilibrium relationship between the non-stationary variables. The non-stationary here refer to the I1 variables, I1 variables. The Johansson test normally used for I1 series. And for the I2, right, we have to use a different configuration test, which is going to handle the I2 series. Okay. So estimation and inferences is complicated because it's like the next week lecture we're going to introduce you the AIDR model. That is a simple, very straightforward. But today we're going to introduce you to configuration. Actually, this is what we say because we involve the system, right? So a little bit complicated. So we need to be cautious about this system approach, right? It's different with the single approach. So remember the step, right? The step there. So we have a system approach to the configuration. We also have a single approach to the configuration. The system approach is a bit complicated, okay? So if we combine the two variables, right, which are I1, then the combination will be I1. So that is the most cases in the majority of the cases. So the two variables here is for example, is independent, what we say the Y and X series. So they are I1, then the combination will be I1. So that is a in this case, right? Most of the case. So in general, right, if we combine the variable with different orders of integration, so the combination of the integration equals to the largest. So for I1, right? I1, right? So that's why for example, if we have the K variable which integrated of order 0, right? So we go to the maximum for the what we say the integrations V, right? Maximum. We go for the integration because the combination, right? The combination will be the go to the this what we say the maximum, right? We'll have the order of integration equals to the largest. So let's say if the X, right, if the variables is I1, so the combination will be I1, right? We'll go to the I1. So that is the idea behind here. So now so there's a definition of the configuration, right, based on this Angel and Granger. So the first what we say the first scholar, let's say first scholar, the idea. So the definition of based on this Angel and Granger introduced in 1987. Then here stated that, right? Here stated that this the Z, right, would be the K times 1 vectors variables. So K times 1, for example, you have 3 variables, right? So it's 3 times 1 vectors, right? Vectors So we have three variables here. Then the component of ZD are the conjugative of order, the D and the B here. So all component Z, right? Your variables are ID lah. So for example, it's 1, so the component of the Z will be the ID, integrated of order D. So here, what we can say that the idea behind Angel and Granger, right? For majority of the time series actually non-stationary. For example, like the GDP series, the money supply series we plot last week. Actually, we can see that majority of these macro variables are non-stationary, but they are moved together over the long run. So in the long run, they are conjugated. There is based on the assumption. This is based on the assumption conjugation. So even though they are non-stationary, but in the long run, they were conjugated. So if those variables are conjugated, it means that if the variables are conjugated here, it means that the linear combination of them will be stationary. So they are moving together in the long run. So linear combination of them will be stationary, right? So here, remember here you have to be conjugation relationship, right? It's known as the conjugated vectors. So the R here will be the R here also known as the conjugated of rank. So this rank, right, normally is less than -1 as compared to the what we say the K, the independence variables. Let's say this independent variable is 3, right? Then the R will be 2 so will be less than 1. If not, right? If not, will be full rank, right? Will be full rank. So that is the you have to take care cannot have some. It's a full rank, it's difficult to estimate already. Okay. Here we usual responder was independent in the first difference of the series of I1 variable. So have no long run relationship, right? Have no long run solution. So the problem with this approach, right, is a pure first difference models have no long run solution. So if you no long run, right, so what happened? So for example, the series is I1, but there is a no long run. That means if you want to estimate such an equation, can we? Yes, you can. You have to first difference the variables. For example, the y and x, actually they are I1. Yes, actually I1, right? So here, the both of them is I1. So they're only stationary once we first difference it. If we want to, if there is a no long run approach, if there is a no long run conjugated, right? So then how are you going to estimate? So before the introduction of this conjugation, right, the idea is we just first difference it, right? Because before we get to know the conjugation test, so we just, for example, the last week lecture, income, the GDP and the money supply is I1, I1, they are I1, both of them I1. So how are we going to estimate? We just first difference the series, first difference the money supply, first difference the income, and then we estimate. So you might want to estimate such a models, right? First difference of Y, first difference of X, and then estimate. But this collection, nothing in the long run. Am I right? So we cannot no long run. There's a no long run relationship between this Y and X. So that's why you one way to get around this problem is to first difference and the level term as well. So not only first difference, we also introduce you the what we said level terms. Level terms means that we introduce you the error correction term here. The yt minus 1 minus the xt minus 1. What is this? Actually, this is a long run, indicate for the long run. It's what we can say is a residual, right, from the original models. So the y and the x, right? So the difference here. So actually it's estimated models, right? Estimated models. So the y minus the xt, yt minus 1 minus the xt minus 1 is known as the error correction term, the ECT. So in actually people just use the ECT t minus 1 as I indicate in the previous one of the lecture, right? I use handwriting one, the ECT t minus 1. That is the that is known as what we say the difference between the y and the x, yeah, minus that 1 period. Okay, so y and x actually conjugated with the coefficient this one with the coefficient here. Actually, with the coefficient, so then this the difference here, right? The difference here, the ECT, actually this error correction term will be I naught. Will be I naught. Even though the Y and the X actually I1, but the ECT term will be I naught. So you can test, right, use the OS on this second equation. You can use OS. For the error correction models, right, we can use the ordinary square approach. The ordinary least square. We use the OS approach to estimate the error correction models. Okay. So in the last point here, the Granger representation theorem, right? Actually, it's a theorem proposed by this Granger. Granger is a econometrician. Okay, this Granger is an econometrician. So the theorem shows that it means that this Granger proposed that any conjugation relationship can be expressed as an equilibrium error correction models. So if we have this conjugated already, so we can use this error correction model to see their short run impact of the X on the Y and the long run based on this Granger causality, for example, to see the beta 2 is significant or not in this equation 2. So how to test for the conjugation? So if you have a more than 2 variables, right? So more than 2, just now we just have a Y and X. So let's say we have a X3 up to X3 up to XK here. So this is a general expression for the models. Here, for this equation 3, the plus plus means refer to others variables, right? Because here we put the XKT. Actually, here got X2T, X3T, X4T. So these are just a general expression. It's a multiple regression, right? So this error, the model for the error correction can be generalized include more than 2. This is just general models. So you can have more than 2 variables which include the X3 up to XK. So this UT is should be I naught lah. If all these variables Y, X2, X3 up to XK are conjugated. So the UT it should be follow the theorem, right? It should be stationary I naught. Okay. So we just want to test if the residue of this equation 3 to see stationary or not stationary. So this is based on the original idea proposed by Engel and Granger. You just estimate the models and then just use the stationary test, or we can say unit test, to test the UT, to test this residue. So we can use Dickey-Fuller as well as the augmented Dickey-Fuller to test the UT. So this UT, right, still can recall last week, right, is the first difference, the UT on the UT minus 1, right, and then with their respective residue in this equation. So we need to use we can test, and then it's based on the significance of this coefficient, right, based on the idea behind the Dickey-Fuller or the augmented Dickey-Fuller. Is use a t-test to test whether the coefficient for the UT minus 1 significant or not significant. But I'm sure that you will proceed to the augmented, right? Because this augmented version is better than Dickey-Fuller, because augmented version will take into account the autocorrelation, right? Which actually is one of the major drawbacks behind this Dickey and Fuller. So why we have a head here? The head here refer to the estimated, because in each equation, once we estimated, we have to attract this residue out. That's why it's called estimated residue. Also, we have the estimated, we have the cap here. We have a cap here, right? Because it's we extract from this equation 3, so it's estimated. So we put a cap here and also the cap on my right hand side as well. So the critical value change also. So we have to use this simulated critical value proposed by the Dickey-Fuller and also the augmented Dickey-Fuller, like what we discussed in our last week lecture. So this is the idea behind this example I used in my previous lecture. So we can you can take a look first, right? So let's say I estimate my models. I have my independent and as well as my dependent. Then I test their error correction term. Then it's based on the significant level of this t-statistic. So this is just one example. Later on, I will show you use the e-views, how we can perform it. Okay. So once I estimate the model, this is my U. Actually, this is my U, right? This is my U, UT. So I first difference my UT and then regress on the UT minus 1. This is referred to the UT minus 1, means ECT T minus 1, that one period. And still remember the idea behind Amanda Dickey-Fuller and Dickey-Fuller is based on the idea behind the t-statistic for this coefficient. So C is negative 2.88. So it's 4 on here. Because I have a 57 observation, right? So my critical value is negative 2.599. And then my test statistic is negative 2.885. So it's 4 on the rejection region. So significant. So I reject the Hirschsprung and Y and M are correlated. I recall back. So I test my last week data based on the income and also money. So let's try. So let's try my data set. Okay. So I take back my data set. This is my Excel sheet. Have you explored my Excel sheet? Not yet. You want to explore next week, right? So okay, I get my data for the money. So as recall, I go to extract my data for my money. Here. So money supply data set, right? So I have Malaysia case. Okay. Then not on the series here, not only the broad money, I also want to have my gross, always say the gross domestic income. I have a 2 data set. So for Malaysia case, so I extract this data set. I make it nicely. And I paste here, paste special, right? Transpose. So this is my M2 series. This is my GDP series. Okay. So my series start from 1964 up to 2020, right? 1964, I start my sample. So it's okay. This start in 1960, right? So I just copy, paste up to 2020, right? Because it's my data set for 2021 is missing for my first series, right? So I copy my series, okay? Then I go to my e-views. Then here I create a new work file. Actually, you can jot down, right, the step, right? And when you practice, then you can get note of it, right? Actually, is it let me see. Yeah. Well, I want to show this one because if you want to download the e-views, right? Because maybe some of you do not have something like the e-views, right? You can go to the e-view student version, right? E-view student version. You just type that e-view student version. This one, e-view student version, like download. It is okay for the e-views 12 or 14. It's no problem one. So once you come here, do you see a request page here? Right, because some of you might want to know how to download the e-views, right? If here is the e-view student version, like download, then you will see your request page, right? Because I understand that when you see the download, right, you straight away come here and then download for the MacBook or download for your Windows, right? So actually you have to request the serial number. Even though after you download, when you install in your own desk, in your own PC or laptop, it will ask you to provide your serial number. So every one of you will have a different serial number, and unless you share your serial number, I'm not sure how it works. I've not tried that before, but you can use your own email to download it. So you just click on the request page here, And then you just fill out the information. You just fill out the information, and then the service provider, the emails will send you the light version within like within 1 hour. They will send you the serial number already. You just fill out your first name, last name, your email, and also university, and then country, then just 7 + 1 = 8, right? Then you just submit, request a serial number. They will send the serial number to your email's address. Okay, this access I want to share you lah. I put this one inside your in your in your chat box, right? In order for you to download later. So remember, request page here. So okay, so because some of you might have a different download page, right? Maybe you have a different download page. That's why we need to standardize our download page, right? So I need to go to the here. You can follow the step to download the emails in your own device. So don't no excuse. Every one of you should have a email software for you to run the analysis. But one of the limitation with this free version, right? It's a free version. One of the limitation is you cannot save the files. There's only one limitation. You cannot save the files, and you cannot copy paste like what I did. But you can print screen. You can use the function here. You see my scissor in my mouse, right? There's scissor. You can use this one to print screen your what we say, your findings, your output for your assignment purpose. Because you cannot copy paste directly from the emails, there's no worry. We just print screen it only. Then you can copy paste the data set and then rerun again as a practice, right? That's only the 2 limitation. Okay. So work file correct. Okay. When you scroll down here, then you can see unstructured and dated. You can see the dated and balance panel. Right. Since I have date, I put dated. And then frequency here. So my data set is in annual basis, right? You see my data set 1960 followed by 1961 followed by 1962. So this is the example yearly data, yearly. So for M2 and GDP, so I come here. So start date is 1960, all right? 1960. The end date is 2020. So once you have the identify start date and end date, then you can click OK lah, right? Because frequency, right, like I mentioned last week, we have so many frequency. You can have quarterly, monthly, bi-monthly, from the low frequency to the high frequency. So now I move from the low frequency. Then actually we also can have the high frequency monthly data as well, right? So you click OK for my 61 observation. If you ask you to update, maybe you can know lah, because changing time, right? But it's good for you to update, right? So I have a 61 observation in total. Okay. Then I go to paste the data. Just now I got copy, right? So now I can paste my data. I go to quick here, and then I need to empty group edit series. Empty group edit series here. Then in here, don't paste first because I want to paste in my first column, first row. I have a variable names, right? Because when you paste it here, just next to the 1960, you will have a missing one observation. And then your result will different, totally different with my result. So paste above the 1960 because I want to include the variable name. So paste. Oops, how come I did one? So sorry for that. Let me see what happened. First time, yeah. Let me see what happened. Oh, maybe I'm not a copyright. Copy. Then I go to my e-views. Then I go to my quick empty group edit series. Then only paste. Yeah, come back luckily. So here, this is my series. That's why you can see E plus 09. Actually, it's not an error. Actually, it's just you have a 90 after 1.65, right? 90 after 1.65. So it's appeared in the Ringgit Malaysia. Because this is a measure in the Ringgit Malaysia, right? These 2 series measure in Ringgit Malaysia. So it's that's why it's because it's a very huge series, so it's appeared in when you enlarge it, it'll be like this, right? So that is unit of this Excel. So once you successfully you double check whether same or not with your Excel sheet, right? If data same, no missing, it means that you successfully paste it. Please double check because student might paste other data set. So you have to double check it. So one is okay, then you can start to do your analysis. So as I promised you, right, today I want to teach you the log, right? Because log the series is the result will be different. Because I want to try to minimize my scale of the series. So I want to log my series, and the formula to log the series will be log, right? Ln M2 equals to log in the parentheses M2. So this is my comment in my previous later. So this maybe I highlight it first now, okay? Why is like this one? Why like this one? Actually, this is command in the e-views, and the series in red color refer to the variable name. Variable name in your Excel. Okay, have to be exactly same variable name in the Excel. So this one cannot change, right? Because it's a variable name in the Excel. And the thing you can change is the green color one. LNM2, LNGTP, you can change. But for my practice, I always want to show because here I only have two variables, right? Two series, right? If I have 10 series, if I give a different variable name, you will confuse myself, right? So I just want to say, okay, I have M2 series, and then I lock the series. I put LNM2. You can put Doraemon, you can put Kuromi, no worry, no problems one. As long as you recognize the news generated series. So if you, because this is original, right? Is original M2 and GDP, they are original series. So if I lock the series, it will be my newly generated series. New variable series, a new series, right? So I can give a different name in order for me to recognize it. So I understand that GDP is my series, and then I lock it. So the green one, this one will be my new series. So I give a name log for my GDP, LN for my GDP. You can put LOG GDP, no worry. You can put Kuromi, you can put Doraemon, depends on your characters, right? But follow my practice first. You put LN2, LN GDP, this is a new variable name. You can change new variable name. The thing you can change only the green color, but the red one you cannot change. The red one have to follow exactly like your Excel sheet. And then the black color one equals to log in a parenthesis. These are the command in the emails. You cannot change also. Okay, so that's the thing. So what is the thing you can change? The variable name you can change. That is your right. But the red color and the black color you cannot change. Okay. So as you see, right, my series here is M2 and GDP, right? So these two you cannot change, huh? So these two is cannot change. You have the same exactly like your variable names here, right? So now I want to generate my series. Generate my series. I go to quick generate series. I go to quick generate series and type my formula. Ln M2 equals to log in the parentheses M2. Actually, the M2 also appear here, right? After I generate, you can see the difference. I can, okay. Before I show you the difference, generate the GDP series also. Before I forget, right? Go to quick generate series. And GDP here. You mean I ask the emails to log my GDP series, and the new name is LN GDP. Okay, done. You want to see the difference? Can. For example, I show you the difference between LN M2 and M2. I open them as a group, delete the original group. So can you see the difference? Can. One is, it means that 1960 for the M2, it's just 21.226, right? But for the M2 is 1.65, and then I have a 90 after 1.65. So it's very huge, right? So if you log the series, this is called log. If you natural logarithm the series, we try to minimize the scale of those variables. This is a normal practice in the macroeconometrics. Okay, it also apply for the GDP, but actually we have a rules lah. We have the rules in for us to lock the series. So we only lock the series if we do not have the negative value. Negative value cannot lock. Maybe I can say only lock the positive value lah. Positive values only. It means that before we do the analysis, we scan through the series first. We scan through the data point first. If we have a negative value, we cannot lock already. Because if you lock the negative value, it will become not available, right? We cannot lock the negative value. We only can lock the positive value, and not ratio lah. We cannot lock the ratio series, not ratio variables. Not ratio variables. For example, not ratio variables. For example, current account over GDP. For example, debt over GDP. Already in the ratio, no need to lock now. Why? Because you already transform a series, right? You measure that per capita. You measure that in the GDP, right? In the GDP ratio. So there is no point for us to lock the ratio series. Because it has a ratio series, right? No point, because it's already very small, right? So because its a current account is in a million, billion, and then GDP also in a billion, so come up the ratio will be like 1.2, 0.5. So no point for you to lock the series already. So there is not the ratio variables, and not the percentage change variables. Why? For example, economic growth. For example, GDP growth, economic growth series. Oops, what happened with my pen? GDP growth series. For example, GDP growth series. For example, inflation. For example, interest rate. Is a several example I can give to you lah. Not in the percentage change, right? Interest rate not in percentage change, right? But this interest rate might fall in the first category. Why? Interest rate, right? Sometimes interest rate can be negative, right? Interest rate can be negative. So some researcher will scan through. For example, Japan also have a negative interest rate, right? So that's why you have to scan through first. So once you found there is a negative value, so we're not going to natural logarithm. Why? Because even though the whole series is majority is positive, only several points negative, we also cannot lock it, because you are going to have a missing. Once you lock it, positive one have a value, but negative several point, 1 or 2 point will become not available. So once you run the result might be have a problems now, right? The result also become no longer precise, no longer valid. Okay. Then how about inflation? Inflation is in the percentage change. If we measure in the consumer side, right? Consumer price index is a percentage change in the consumer perspective. So inflation sometimes also can have a deflation, also going to have a negative value. So normally percentage change variable, we advise not lock it. GDP growth series also no. GDP, right, in the growth in the percentage change already from my GDP series. So the GDP growth rate, I'm not going to lock it as a perspective of the researcher, not going to lock it. Because, for example, like the Malaysia case, our GDP growth actually is negative, especially during the 1997 Asian financial crisis, right? If you plot our economic growth for the Malaysia case, we have a negative value somewhere in when the outbreak of this Asian financial crisis. Okay, so not percentage change variables. So what else? I think is these three not we only can lock for the positive value, and then not the ratio variables and not the percentage change variables. Okay. So that is a certain rules for you to follow when to lock the series. So if you plot it, right, if you plot them together, you go to view, you go to graph. Also they have a same pattern, same trend. If I use the multiple graph to show them together, right, to show them, right, actually you also have a same trend, right, same trend, but it's a different scale. right? 20 something up to maximum 28 point something, for example, instead of million, billion in ringgit Malaysia, okay? But there's a difficulty part, not a difficulty part, when we interpret the result, have to be careful. This you learn in your applied econometric, right? Yeah. So when you, in your basic econometric class, different functional form will have a different interpretation, right? Because the coefficient, when we have a double log models, you're going to have a different interpretation because we are measuring the percentage change, right? We're measuring in the percentage already because we can straight away get the elasticity from a double log models. So there's a difference. So if you want to know more about the interpretation, you can try to take a look the explanation. It means a different explanation for a different functional form. Actually, we can have a different functional form. What I'm going to introduce you today is a double log models. Actually, you can have a linear functional form. I can have a double log models. I can have a log linear. I also can have a linear log models. Different functional form. We can have a more exposure on that. Okay. So now after I log the series, actually what I want to I go to so far already, right? Yeah. About this co-integration. So for these two, right? So and then I want to regress them together. I open them as a equation, right? Ln2, Ln GDP, So I start from 964, right? So I want to same like my case like my result show in the slide. So I just estimate. So I obtain this result, right? This is my OS result, Ln2, and then Ln GDP. So this is my result. So the result here is want to test for the ECT, right? Yeah, ECT. So what I can do here is I need to extract the ECT, right? So how to get the ECT? Actually, you already get it. Actually, the residue. The residue will be my ECT, right? Another way to extract the residue out is go to the prop. Go to the prop and then make the residual series. Go to the prop and then make the residual series. And then the name for this residual, you can call it as a ECT, right? ECT. Then you click OK. That is in my ECT series. My the difference. Actually, how we get the error the ECT. Actually, it's a y minus a y hat. Yeah. So how to get the error correction term, right? So some of you might confuse how I get this residual. The residual, right? Sorry. The residual actually is equals to y minus the y hat. Maybe in my case here, actually it's m, right? It's m is Ln m2 minus the Ln m2 hat. So this is how I get my residual. So the difference between my my dependent variable and my estimated variable will be my residual. Okay. So this is my ECT, right? So what is the idea behind the Angel and Granger? In my previous slide, we have to first difference my residual regress on the ECT minus 1. It means the residual T minus 1. So I need to type my models, right? So what is my function here? So I can use this one different for my ECT and then regress on this ECT minus 1, right? So this one just put that, okay? So let me check. And then with a constant, right? Yeah, with a constant. Depends on you. If you want to test with a constant or not constant, right? So in my case here, I want to test for the constant here. So I can put a C also, right, in my models. So you just run simple regression now, right? So this is my function. So first difference my ECT regress on the ECT minus 1. So the idea behind the Dickey-Fuller, right? The idea behind Dickey-Fuller is use the t-test to test the coefficient for the ECT T minus 1. So I go to my eViews, go to the quick, go to the estimate equation. I just type my models. So type my command, okay, not model, type my command. So the first difference for my ECT and then C and then ECT in the parenthesis -1. So you just start from 1964, then you click OK. Oh, I think a little bit different, right? Because here is 1965. So it's okay. My example here a little bit different because I think I start at 1964, right? So this 57, this 56 adjustment. I think I start 1963 in my whole sample in my previous semester. So no worry about that. So I just want to show you how it's run, right? So it's something like that. So negative 2.165. Negative 2.165 is my test statistic. So you can just copy paste, right? If you have a valid version, copy paste. If you do not have, you just print screen, right? If you use the student version, you just print screen this. So you can show in your result. So I have one more slide to go. New slide and this, right? Yeah. So you can check check with the degree of freedom. I think not much different. Negative 2.599. Negative 2.599. Actually based on the T table, right? T table. Negative 2.599. So same, right? It's like this, same idea. So oh yes.
Victor, I have a question. So why are you estimating the difference of ECT with ECT of the lagged value, not the difference of the lagged value?
Oh, you mean this one, is it?
Yeah.
Yeah, because based on our lecture last week, this is the unit root model. So unit root models, right? So unit root model, we have to first difference my series and then regress on the ECT T-1. Yeah. So it's not the vector, it's not the error correction model, it's not the lag series. So this is the idea behind the unit root. So given us the significance on this variable, so it means that there is a correlated gradient in the long run. This is the idea proposed by Andrew and Granger. So we first define the ECT and then regress on the ECT T-1, the lag one period for the error correction term. I mean the residual here. So that is the how's the unit root models idea, how we test for the stationarity of this residual series. Yeah, because the last week we just for example, like this case, right? Let me show you. Last week we just double click on, for example, for this M2 series. I go to view and then I go to this unit root test. I use the standard unit root test. Then augmented Dickey Fourier, for example, okay, with the intercept and the level. Then I click OK. So as you observe here, this is ideal. So this one, based on augmented Dickey Fourier test, you first difference this series, right? M2 series, and then regress on the lag for the M2 series. So now, based on this Andrew and Granger, we test the co-integration, whether there's a co-integration or not for this M2 and also GDP. So the idea borrowed from this unit root idea, we first difference the residual for my regression and then regress on the lag for my residual. And then use this one to compare with the critical value, whether significant or not significant. If significant, then in this case, for my M2 series, there is a stationary if significant. But for my case, there is a co-integration. So the idea is borrowed from here. So something like this, right? So it's we can use this Dickey Fuller or augmented Dickey Fuller to test on this residual. That's why it's first difference my residual on the UT-1. So I think okay, right?
Okay, but like conceptually, like what does it actually mean? Like so I'm a bit confused on what does it mean to estimate a difference of the residual with the lag of the residual. So that's the part that's a bit confusing.
Okay, no problem. Let me show you this one. Yeah. 。
Okay, 。
So 。
So 。
So 。 So 。 So 。 So 。 So 。 So 。 So 。 So 。 So 。 So 。 So 。 So 。 So 。 So 。 So 。 So 。 So 。 So 。 So 。 So Let me get back my. Yeah. You can see my screen, right? So this one. Yeah. So actually, this is the how do we test for the unit root, right? Like this one. This one is in the slide 26 last week. So this one, how we test for the unit root. So this is the general idea, right? So the objective is going to test whether the YT and then on the YT minus 1. So we test this rule, right? We test this equals to 1 or not. If less than 1, then we say there is a stationary, right? If it means that if the test significant, then we can say the series is stationary. But we cannot test this one. So we usually actually is similar idea. We use this regression. So we first difference the YT and then on the YT minus 1. So to test this one equals to 1, actually is equivalent to test the coefficient for the YT minus 1. Is it equals to 0 or not? So this is the how we test for the unit root, the series, whether stationary or not stationary, based on this unit root idea. So actually equivalence, because you move this YT minus 1 here, right? First difference, right? Actually, actually it's difficult for us to test whether equals to 1 or equals to 1, right? Restriction, right? We want to test whether equals to 1 or equals to 1. Actually, we can just first difference the series, then test whether the coefficient for the YT minus 1 significant or not significant. So it's equivalent. Okay. Is it okay? Okay. So I'm back here. So we can compare, we can check for the critical value, then see whether the series here, is it fall in the rejection or not? So where's my pen? So it's based on it's not based on the T table, right? So we check what is the critical value here. So I think it's fall in the rejection also, right? Negative 2.165 as in my different sample, like 57 sample, right? In my previous example here. Yeah, adjustment. Yeah, it's based on this one, right? This one is Angel-Granger critical values, Angel-Granger critical values for co-integration. So you can test for the constant, no train, and then constant with the train. So this one I get from the internet, especially for the Angel-Granger critical value for co-integration test. It's different now with the augmented Dickey-Fuller, because augmented Dickey-Fuller is used to test for the whether series is stationary or not stationary, right? For the augmented Dickey-Fuller for their critical value. But this one is an Angel-Granger critical value. So they're simulated for the up to more than 500 observation. So it's much more, if we have a more than 500, then you just use the standard one, right? The standard critical value. But if you have like my case, small sample, for example, I want to test like in my first case here, I test for 57, so I use negative 2.599, right? So negative 2.599 means I refer to somewhere around here, right? Where's my case already? So 2.599, I think here, yes. I test for whether we have a co-integration at 10% or not, right? So if let's say my one is like 56 or 57, right? So I also can use 10% to test whether there is a 10% significant or not critical value. But conventional one is negative 2.9, right? Negative 2.95%, negative 2.921. So here, if let's say it's negative 2.921, so my actually not fall in the rejection, right? I fall in here. So actually there's a no co-integration because it's fall in the non-rejection region. Non-rejection region. So it's no co-integration in the long run for my case. So how about this one? So now the negative 2.599, right? For my previous case, negative 2.599 is here. But my critical value under this scenario is negative 2.8. the test statistic is negative 2.886. So it's fall in the rejection. So there is a co-integration amongst this Y and M. But for my case, once I adjust the sample, right, just a little bit adjustment, so there's a no co-integration already, right? Even though I use the 10% critical value, negative 2.599 here, negative 2.599 also no co-integration. So you can see that the sensitivity of the result, right, by just a one observation difference. So there's no co-integration. So you can say no co-integration in the long run. So we can just now I show you the table, right? Actually, it's a critical value. It's a new set critical value, and then Andrew and Granger name their test as an EG test, not the ECG, right? It's an Andrew and Granger test. So the EG test in 1987. And then the H now, right? Just now actually what we test. What is the hypothesis? It's a uniroot in the co-integration, and the residual actually stationary. Because we're testing the residual, right? The difference between the estimated models and also the real observation, right? So the residual here, just now I name it as an ECT, right? ECT. So the ECT whether is an I stationary or not stationary. So if you fail to reject, there is a no co-integration because the residual actually has a uniroot. But now if I reject it, then the residual actually are stationary. So these are hypotheses. So bear in mind that if significant, then there is a co-integration. So the residual actually from this co-integrating regression are stationary. We can make this conclusion. If let's say my case just now is failed to reject, right? So no co-integration. So we can say no co-integration. There is a uniroot in the co-integrating regression. So if like that, right, what I can proceed is I just proceed with the no co-integration, right? By the series I1. So I can proceed with the while if you want to test for the short run, but no long run because there is a no co-integrated regression. So there is a no long run. So I only can test for the short run. Okay. So there is three methods actually. There are three methods we can test for the co-integration. First is the Andrew Granger that I introduced you just now. Another one is the Andrew and Yu. Andrew and Yu. And then the third one is the Johansson. The Johansson is a bit different. The Johansson is a system. So this Andrew and Granger is similar like the ARDR. We're going to introduce you the co-integration. There is also a single equation, but ARDR is much more not say recent. It's introduced you in 1999. So a little bit different compared to Andrew Granger. Because Andrew Granger is quite it's an old version of co-integration. It's somewhere in 1980 something. So the recent one actually take into account the limitation in Andrew Granger. Okay. Later on we will take a look what are the limitations. So in the step number one, right, you have to we only can apply this Andrew Granger where all the variable I1. Not rational, right? Only the I1 variables will test for the further to co-integration. So I1 variable, then we want to use the co-integration test to see whether there is a co-integrating regression or not. Okay. Then we estimate the co-integrating regression just using OS. Then we save the residual, right, the UT just now, and test the residual to ensure they are I naught, right? To ensure they are I naught. If they are not I naught, then we no need to proceed, right? We just stop there only, right? If they are I naught, if there is a significant, right, then we can form our error correction models. So we can form our error correction models. So how to form the error correction model? We first define the Y and the first difference the X. Because this error correction model is different with the co-integration test because in this first step, we first define the residual, right? And then regress on the constant and then regress on the UT minus 1. Am I right? So that is a different. So we test the coefficient for the beta 1 here. So no, sorry, it's not beta 1. It's test this one, the residual, right? Test the residual. Yeah, test for the residual. Yeah, test the residual. Correct lah. Sorry. This sorry for this one. I don't think it's this one. I think it's testing for the beta one. Testing for the beta one, right? Yes, testing for the beta one. This one. Sometimes I also confuse that. Testing for the beta one. All right. That's the idea behind the unit rectangle. Then, if we found their I not significant, then we can proceed to the error correction model. So the error correction model will be changes in the YT on the changes in the XT, then also together with the ECT, but not its error correction term. Is the ECT T minus 1. Is the ECT T minus 1. So we're testing this one. So actually, we can use this one to see the causality, right? Yeah, causality also. We can use this one to test for the long run causality. Whether is it drive from the X to the Y or not. Long run causal from the X to the Y. Then you will ask me, can I test the long run causal from the Y to the X? Can. We can test, but you have to change that. You have to change your error correction models, right? You have to rerun for the step 1 and until step 2 also. So in the step 1, you have to run the models with the X as a function of the Y, then get their residual, right? Get their residual and then regress the residual again on this leg for the residual. Then only go to the another set of the error correction model with the XT. And then again, on this as a function for these changes in the YT minus YT also, right? And the YT, and that also together with the ECT also, T minus 1, to see whether there is a Y to the X or not. So this is another set. So you have, because you are testing single equation, right? So you have to run, repeat the step again to test whether there is another way causality from the Y to the X or not. Okay. So this residual, right, actually like what we mentioned, but like what we did just now, the residual actually from the YT minus 1 minus the XT minus 1. So actually it's this is from an estimated model. From an estimated model. So actually the residual is obtained from the Y minus the Y hat. And then Y minus the Y hat now, right? After that, you let one period. You let one period. So it become like this. But they use this as a X hat now. Actually, it's estimated models. Because I only have one, right? I only have one variables. So they use the X instead of Y. So this is a critical value. So approach causality. So these are basic error correction models. Okay. So we have the example. This is an example in the classroom discussion. So how is what actually? You can see this error correction model. So we have what? Changes in the YT, and then changes in the YT minus 1, then changes in the what we say the ST minus 1. And this refers to my error correction term, my residual T minus 1. Actually, error correction term means refer to the residual T minus 1. It's referred to the error correction term here. Okay. So in the parentheses refer to the standard error. So these are the standard error for each coefficient. Standard error. So the question is there any evidence of co-integration? Right. So there is evidence that. So if we found out that the variable actually is I1, right, for the Y, for the S, there's I1 already. Then we test the Angel and Granger. And if there is a co-integration, then we proceed to the ECN. So this ECN, so can we use this, as we said, I can test for the long run causality, right? Yes, long run causality, how to test it? So the long run causality from the S to the Y can be tested by using observation based on this ECT. So if the ECT is significant, then there's a long run causality between the S to the Y, from the S to the Y. There is a long run causality if the ECT is significant. As we mentioned in the early slide, right, it is not workable for the multivariate, because if we involve more than one variable, for example, j variables. First difference for the j variable t minus 1, for example. I have a 3 variable, for example, not only y, I also have s, I also have a j, and then the ECT is confusing, right? I don't know which variable go to y already. So it's not workable for this multivariate like we mentioned, highlighted in the first few slides. So how about short run? Is there a short run causality? It's insignificant. Why? Short run causality from the s to the y. So this one, right, coefficient, and this one. So is significant, not significant? This only one leg, right? If we have the more than one leg, that I have to use the word F test already. But this one just have only one coefficient, 0.9, only 0.9. So I can just strip away, right? The test statistic will be 0.9 over 0.9. What you will get? 1. Because I need to use the coefficient divided by the standard error. That is the test statistic, how we form a test statistic. So that's why statement here, key ratio equals to 1. So it's not significant, right? It's totally not significant. So there's no short run. So already no short run, right? How about, do we have a long run? Yes, because long run will be 0.7 over 0.1, you obtain 7. Right, the test statistic will be 7. So there's a long run causal from the s to the y, but no short run, right? Because the insignificance of this, right, these changes in the s. So how about the multivariate? The multivariate, right? This is just a single equation, right? How about the multivariate? So we have the same like the test for the single equation, test the variable for stationarity using the just a usual unit test. If all the variable are 1, then we have to test whether there is a co-integration or not. So we can use the AIC or the SPC, the SCORCH, the information criteria. This AIC AIC refer to the AKG information criteria, and the SPC refer to the SCORCH initial information criteria to see the number of lags in the co-integration test, the order of bar to check. Because just now you also see that, right? Just now you also observe that, right? Only one observation. Actually, we have a co-integration in 10%, but just a one observation difference, then the result become no co-integration, even though at 10%. So also the co-integration test also sensitive with the number of lags. So how to avoid means that our result not something that not questionable. So we need to have some baseline to justify how many lag you are used to test for co-integration. So we need to use this model selection criteria. For example, the information criteria, AIC or SPC, to determine the number of lags. Okay. So under this Johansson, we have a two statistics. One is the trace, the other one is an hygiene test to see number of co-integrating vectors. So no full rank. If there is a full rank, something wrong with your models. No full rank. So your R have to be lesser than your K. Okay. So no full rank. So after we test for this trace and hygiene value, if there is a co-integration, right? So we can see their long run. We can see their long run coefficient and the adjustment coefficient. This adjustment coefficient refer to the ECT. Adjustment refer to the ECT to see the long run coefficient, what is the long run impact of the income or the money demand in like our example, and also to check for their adjustment as well. Because the VCM, right, for example, in my case, I also going to have a two endogenous variable. That takes them to become an endo, right? Income and also the GDP. So you can use to test the gradual causality over the short run and long run based on these endogenous. You're going to solve the challenges in your Engel and Granger, which is based on single equation, right? Based on single equation. So that we can use to check for it. So the test we're going to introduce is a Johansson. Okay, Johansson. It's possible to obtain more than a single co-integrating relation. Why? if there's a more than one co-integration, relation, which one should be used, right? So so there is one of these what we say you need to what we say constrain the models in this system co-integration. This is multivariate approach. That's why the single approach, especially to deal with this small sample size, because with these challenges in the system co-integration approach, Johansson, especially the Johansson one, and also because of the small samples, for example, in my case, researcher like the Pesara and all try to propose a new approach. There's a single equation to solve the system problem, especially if you have the more than one co-integrating relationship. So which one you should use, which model, which equation you should use. Which equation means that which is the correct dependence variable, right? Dependent variable because I'm focused on the money demand. If I have a two co-integrating vectors, let's say I have a three independent three variables. I have interest rate, income, and money. If I have a two co-integrating relationship, so which actually is my dependent variable? Is it money, supply, or interest rate, or the GDP? So there is a that's why you need to have a little bit complicated by using this system, a little bit caution also, right? And there are two separate tests here. This multi-variate approach, there are two separate tests. It's an IGene and also the even trace, right? Trace and IGene, and sometimes will give a different result, right? And also, what we say, if you compare, right? If you compare with the Andrew and Granger, just now I have a single equation, right? Approach to the co-integration. Yeah, it is indicate that there is a co-integrated with 10%. But when I use this multivariate approach to co-integration, I found no co-integration. So which will give us different result as well, right? And this given this maximum likelihood based test is required the large sample size. Large sample size is a maximum likelihood ML based test. The Andrew and Granger we used just now is based on OS, right? It's just based on the orderly square approach. Like I just use the OS to run the regression and then extract the residue and then use the OS again to test the significance of the lag for the residue. But for the Johansson, it requires large sample. Yeah, so if you want to use the Johansson to test for your analysis, to test for your means for your variable to achieve your objective, you have to make sure your sample large enough, okay? And this multivariate case is based on a VAR, not single equation, okay? So you have to handle the endogeneity issue as well. So these are based on the VAR approach, and then all the variables are assumed to be endogenous. So that's why you can refer to my paper I show you. I also uploaded in the Spectrum, Check et al. 2009. Although it is possible to include exogenous variables, but all the variables assumed to be endogenous because it's based on the VAR approach. What is a VAR approach already? It's a vector form, right? In a vector, right? So your variables can still become your dependent variables. All right? Just now, still remember that I have something like a brief discussion on the VAR and VCN, right? So the VAR one, your YT, then followed by a ZT, followed by a JT. So all the variables assumed to be endogenous. So which are the correct equation? Endogeneity, right? So, and then the test, right, rely on the relationship between the rank of the metric and its eigen's value or the characteristics of roots. So it's we will see that means that the rank of the metric. So for example, yeah, only have one co-integrating vectors, then only one rank, right? So that's why only one equation, one endogenous variable. That is a we can identify. Oh, I'm very clear that my money supply actually is endogenous variables. So I can provide a very clear policy implication to the policymaker. If I have a two co-integrating vectors, then actually what does it mean? Right? If I have three, for example, four, so that's a problem already. So that's why it's we have to be something like precaution now. Okay. So the approach, right, to test for the multivariate is similar to the ADF, but required to use a VAR approach. And the details you can the detail is something idea like behind the ADF test also like the XT on the XT minus 1, and then you have to test in the changes for the XT and then of the XT minus 1. So we're actually testing we write it up. So actually we're testing this what we say this pi, right? We're testing this symbol, right? So in a system of the G variables. So we are testing this one. Actually similar idea, right? The changes in the XT on the XT minus 1. So we are testing the significance of these variables. Okay, so it's a much more complicated lah. So testing, right? Using the Johansson techniques based on the VAR. So we need to turn to the VAR formula. Okay, VAR form. So it's in the vectors, right? So G times 1, it depends on how many variable you have, right? So it's G times 1. There's a G times is a G times 1 for the XT minus 1, XT minus 2, as well as the G. It means that the G for this UT, right? UT also. So it's how many, it depends on how many observations you have also, right? How many observations you have. So it's a present in the VAR form. Present in the VAR form. So how many observations that depends, right? It's a G times 1. So this we are testing for this lag, right? We're testing for this lag. So it's here we are testing for this one. So we are not going to become very complicated. We just want to understand that we are going to have a two-test statistic, right? Where is a trace, where is a hygiene, right? Have a two-test. One is this one. Where's the test? Trace and also the hygiene values. So the idea behind make it simple, the Johansson is based on the VAR approach, and then the idea is similar like this. Want to test the rank, right? So the rank here equals to the number of coordinating vectors. So this rank, right? This we want to consider of all the 0. So with the ADF test and the metric equals to 0. So there's something like implying the variable actually no coordinated. So if there is a not significant, right? So there are no coordinated. So so similar like the ADF, the equation, right, also got the lag dependent, and then the lag increase is important because it's going to affect the result. Like the case like I show you just now, the observation also will affect the result, right? So this Johansson also sensitive to the result. So you need to have based on the suggested lag. That's why we can say it's an optimal lag length. To ensure the optimal lag length. So how to ensure the optimal lag length? Based on the information criteria, AKG or the Scotch patient criteria to get the optimal lag length. Okay. So what is the difference here? What's the main difference compared to the bivariate, compared to the Angel-Granger? So it's possible to obtain more than single coordinate. So as my point number 1 here, it's possible to have more than single coordinate relationship. Why? Because you allow all the variable have a potential to become endogenous, right? So you have potential to obtain more than single co-integrated relationship. But you only can have one only based on Angel-Granger because it's based on single equation approach, right? It's based on single equation. So if there evidence of more than one co-integration, which one should be used with the Johansson, right? That's why we have to be I think there's a solution discussed in the research also. You have to restrict the variables, restrict the equation in order to get the one co-integrated relationship. But you will give us something like the very blur policy implication, right? If you also don't know how to interpret the result, right? Because you have more than one. So you have, for example, in my case, I have 2 co-integrating vectors. So which one to use, right? So you have 2 separate tests. There are 2 separate tests for co-integration, right? For this Johansson, we have 2 separate tests, trace, right, and also the engine. So it will give sometimes will give a different result, but only one with the Angel-Granger. So Angel-Granger just to show significantly, right, based on the UT minus 1. So only provide you one result. So you might be come up with a misleading findings with the Johansson, especially when they have a come up with the difference findings from the two separate tests. Okay. And this Johansson require large sample and multivariate based on the one, not the single equation like the Engel and Granger. So you need to know the differences, the main differences between these two approaches, right? And this one, when this R equals to 0, then there's no co-integrating vectors. Okay. If there are G variables in the system, it means that, for example, I have a two variable in a system, right, of an equation, then the maximum of 2 minus 1 is only have one co-integrating vectors. Okay. For example, if I have an M and income, money supply, and also the income in my system, that I only can get maximum of one co-integrating vectors. Okay, it's -1. Have to be -1. So general G, then G minus 1 co-integrating vectors. So if G equals to 2, if the co-integration exceeds, then the co-integrating vector is unique. Because it's a full rank, that's the problem in our estimation, full rank. Okay, so there's the details for us to test for this co-integration. Okay, so there are two test statistics produced by Johansson, trace and hygiene. Both can use to determine the number of co-integrating vectors. Yeah. So these are the two test statistics. So for under the Johansson test, one is based on the trace, another one based on the hygiene. Okay. So so what is the difference here? Right. So it's a test the number of co-integrating vector less than equals to the R against the unspecified alternative. So that is it's different. Actually they're testing the same thing, whether there's a co-integrating or no co-integrating, but they have a different now. Okay, so it's testing the now of a number of co-integrating vector less than equals to the R against the unspecific alternative. Then how about the max, the hygiene one? Test the now the number of co-integrating vector R against the alternative R plus 1. So there's a different unspecific alternative against the R plus 1. So that is the difference here. So and then maybe make it in the sentence, right? The difference, right? The trace, right, is a joint test. It's a joint test to test against a general alternative. They are more than the R. But the hygiene one is for example, alternative, there are R plus 1%. Okay. And there's a difference between these two statistics. So testing against more than R, as well as under the hygiene, R plus 1. So what is the distribution? Distribution for the both tests is the non-standard, not follow the standard distribution. So let's take a look at this example before we move to the hands-on, the stock price and the income. The stock price and the income. So I have the S here as my stock price for our so I'm still here. Yeah, I'm still here, right? Because I think something a little bit sound, right, for my desktop. So okay, so for this case, I have my stock price and then I have my income. Okay, I have my stock price and my income. Then I want to test whether there's a co-integrating or not for these two. So let's say my trade statistic is 40.3 trades, right? So and then the trade test so it's a trade test, right, against the alternative is less or equals to 1, right? And then against the alternative general one more than the R. Okay. So here if compare, I have to compare with the critical value. Compare with the critical value 20.5, 20.2. So only one significant, right? So that's why we say only co-integrating in the one vectors. Only this one significant. Okay. Only one significant. How about the based on the hygiene? The hygiene one is against alternative R plus 1, right? So 0 and then R plus 1. So it's 0 plus 1 here. And then this is 1. So 1 plus 1. Okay, right. So this one is actually is more than is a different, right? Different hypothesis under the trace. But you can see a difference for the hygiene, it's just a R plus 1%. So it's testing 0 versus the R equals means R equals to 0 versus R equals to 1. So it's significance, okay? So we can say that it's reject the Hirsch now. So it's only one vector, R equals to 1. So R equals to 1 under this case. But this one is less, right? Less than 9.2. So we fail to reject. So fail to reject means R equals to 1 in this case. Okay, only one vectors. So we can say exceed the critical value when the R equals to 0. So we can conclude that at least one co-integrating vector is present. Okay. So how about for more than one co-integrating vector is less than the critical value? So we can say only one co-integrating vector is present. So that's why we the important thing part is interpretation, right? So if I provide you this type of statistic, if you don't know how to interpret, so it's difficult also. So if you interpret the result, we can say there is at least one co-integrating vector is present. So how about the VCM, right? The vector error correction models. So it's we have additional variables, which is error correction term, is inside the model, inside the var. So imply that the appropriate VCM can be formed. So just like a basic var, but with the additional error correction term. Why we need this error correction term? So there's a reason here, because it measures any movement away from the long run equilibrium. So what we can say that given us a significance of the error correction term, then we can say there's a long run equilibrium. All the variables move back to the equilibrium in the long run. Okay, so they are often used as a part of the multivariate test for co-integrating, such as the Johansson. So evidence of the I1 variable, then you can use to test for the short run and potential grandeur with the VCM. So we can use this VCM to test for this short run as well as the potential grandeur causality. So what are the criticism? Criticism for this Johansson? Sensitive to the number of lags, right? And the presence of autocorrelation, because once we include the lag, there's a possibility of autocorrelation, because for example, the YT, right? The YT -1 and then YT -2. So there's a potential of the autocorrelation. So if let's say more than 2 co-integrated vectors, so how do we find the most appropriate vectors, right? So which is the correct endogenous variables? So we have to do the additional step to get the much more valid result, right? And given us the trace and hygiene value, so which one will give the correct result, right? Is it only based on the trace or is it based on the hygiene, right? So, and then this is for the large sample test. And the Witten critics suggest that we often find the evidence of co-integration when non-acid. This is the Witten critics. This is critics proposed by Witten. Actually refer to the misleading result lah. Even though we found there is a co-integration, actually should be no co-integration. There is a proposed by Witten. You can get to know more about the critic by the Witten. Okay, so now let us go to have the something like estimation by using these e-views. So before maybe we go through the step here first before I move to the e-views now, okay? Because difficult also to show two screen, right? So how to estimate with the e-views, right? So let's go through the data set first. So I need to use the Broad-Money GDP, GDI, the gross domestic income, right? And the DIR. So data in the Excel. Then you have to create the work files, start from 1960 to 2001. I just go to the maximum. I just let the e-view to choose, even though my observation later will just stop at 2020. Then in the e-views, right? Like we introduced just now, we copy paste the data, you go to the quick empty group edit series, and then once you paste the data, you need to generate the series, right? You need to lock the variables. This is a different name, right? Even though I use this one cannot change. This one cannot change, right? This one cannot change because it follow the Excel sheet. So if you just follow the Excel sheet, you just follow lah, right? And then this the blue one you can change. Then if you want to estimate, let me start with the two variable first. I estimate the log L money constant. The C here refer to the constant. Okay. C here refer to the constant and then log for my income. Okay. So I estimate the double log models. Then before I estimate, I can plot the series, right? Then I found this result. Y as my dependent variables. This is my dependent, right? Dependent variable dv, dependent variable here. I use the method least square, right? Then Angel Granger. This I show you just now, right? Angel Granger, right? So after you estimate, you need to generate the residual with the prop. So we run already now, and then you name it as an ECT, and then perform the ECT with the ADF test. So with ECT, right, you also can use this way. Actually, it's similar lah. If you use the unit test on the ECT, it will create the similar result, right? You'll create the similar result also, right? So actually we return back here also, right? Then you compare with the critical value, actually insignificant, right? Insignificant based on this 60 observation. Again, it's different sample size, 60 observation. So insignificant, because you cannot based on this p-value. You have to compare with the simulated critical values, okay? Based on this ECT. So it's a significant, right? Yeah, significant, sorry, insignificant. Fail to reject. Fail to reject because it's greater than the critical value 10%, right? So you fail to reject. So fail to reject means that your ECT has a unit root. So fail to reject. So less than the critical value is based on Angel Granger critical value table. The table is not significant at 10%. Fail to reject. So the residual from the current declaration relationship are not stationary formulation case. Okay, so this is how we interpret the result. So how about how we can conduct these error correction models? This one I haven't shown you, right? This is a command. So this is my variables. I start single equation approach, right? I start with my money, right, as my dependent constant, followed by my independent, but variable have to be in first difference. The D in the E views is a first difference in our equation here, first difference. So once I first difference, you can try to perform yourself for your case, right? The first difference, type this command is continuous, continuous one because of the space, right? It's continuous one. So here, coefficient negative 0.094. So, and then the test statistic negative 1.60. Then this follow the standard distribution, right? So you can compare with the 1.96 at 5%, right? Or 1.645 at 10%. So actually it's even though at 10%, negative 1.645 actually is not significant. Why? Because you will draw like this, right? Negative 1.645. So this one negative 1.60, so it's put in here. But this is rejection. But negative 1.60 is fail to reject. Fail to reject. So we can say ECT not significant. So no long run causality from the income to the money. Right? So no long run causal. So how about short run? Short run, we have to look at just the changes in the income. So coefficient here, 2.30, significant at 5%, 0.05, right? Because the p-value here is lesser than the alpha value, lesser than the alpha value. What happened? My pen is boycott me already. Let me click something. Okay, lesser than the alpha value 0.05. Right, so it's significant at 5%. So we can say there's a short run causal for the income to the money. If I want to test the long, whether there's a feedback or not, I have to turn, I said just now, right? I have to turn the models, right? here you have to change become income, and then here become money. And then ECT also have to rerun again, right? With the income as a dependent, money as an independent in the first stage. So like this, you change the dependent variable to the income, and then run the OS, get the ECT, and then check for correlation. If there is a correlation compared with the critical value, is there the correlation? Then you can test for the short run and the long run. So same idea. You can perform yourself, right? And I'm sure you can. Practice, make it perfect, right? So how about Johansson? Johansson and Jussowitz. That's why I call JJ test. Just now called what? Just now called EG, right? Yeah, just now it's called EG. So EG versus JJ. So first thing in the JJ test, check for the lag length. So the lag to include is 5. So how many lag is proposed? 1. 1 lag, right? Based on the AIC is 1 lag. Later on, I'll show you how to search, get this page, 1 lag. So how to look at it? Based on the star. So the star here indicate the lag length selected by the criterion. Okay, by the criterion. So it's just 1 lag. So based on this criterion, lag 1, because lag 1 is significant, right? Based on this AIC and SIC also lah. If I based on these two, actually there are so many other tests lah, like the finals, what is called final prediction errors. Actually, it's called ACCIC information criteria, Scotch information criteria, Anand Creek information criteria, right? So actually, the smaller the value, the better the models lah. So based on these models, and then the for all these models, then based on 0 lag up to 3 lags, then the e-views actually suggested that with the lag 1, it provide the models with the minimum AIC, minimum SIC. Minimum, right? Minimum amongst these 4, right? Among these 4 choice, this is the minimum, right? Lag 1. So that's why I estimate the lag 1 for my case. And then is the VCM, okay? Then VCM, this is my long run result. But when this long run is the overturn, means the income has a positive impact on my money. Have a positive impact on the money. And then significance, okay, this is long run. How about short run? Error correction models, right? Error correction models, are they significant? It's only significant with the bracket one. This is standard error. Parenthesis is standard error. With the bracket one, negative 2.125. So you can compare to the similar critical value. Actually, follow my convention, right? 1.96 is for the 5%, 1.645 is for the 10%, and then 2.645 is it 2. I think 2.57. I also forget. I think 2.5 something. Sorry, I need to log in. How to get out? Okay. Cannot log out yet. Okay. And then 2.576 is for 1%. So I based on convention, even though my sample is 59, right? So if you want to have a more precise one, you can compare with the simulated critical value based on the T table. This one for the T table, okay? From the T tables. So this one significant, right? This is significant. And this one not significant because it's a negative 0.069, right? This is based on the error correction term. This called-in equation 1 is actually referred to the ECT, T minus 1. Okay. So this is a test statistic. Later on, I will show you. This is test statistic. So I just want to show you the result first. These are the test statistic, engine value, and the trace statistic. So very weird also. Can you see? At most 1, right? At most 1 reject. So 1 contributed. Not say weird, consistent, right? I already can say consistent. Sorry, I used my wrong word just now. Consistent result. Only 1 contributing factors, right? Because you reject, right? So at most 1, so only 1 contributing factors. So just like the funny also, right? You suppose this one significance, yeah, weird also, right? Is because it has something like difference, right? We suppose this one significant. this was not significant. But my result is the other way around, right? The other way around. So a little bit weird, right? Two conjugated vectors, right? Yeah. So, but this one is not significant, right? But if this is 5%, right? If I base on 5%, no, actually, this is based on 10% p-value. So either one, actually, in the research, right? Either one. You compare with the critical value or you compare with the p-value. If I compare 5%, right? Actually, my test statistic is insignificant at all, right? There's no correlated in the long run, right? But if you base on the p-value, it's quite weird now because this one all significant, but this one significant at 10%, right? So if I base on critical value, I can say actually there's no correlating. No correlating, then okay, so I cannot proceed with the VCM, right? So I can do this causality, right? Causality based on this WAR form. So I can use this Granger causality. So actually no Granger causality based on this result, right? No causality. Why? How to see it? Because this is my dependent variable and this is my independent. For these models, the p-value is insignificant. The p-value, PROB refer to the p-value insignificant. When I turn my model, dependent is the changes in the income, and then my independent is changes in my money, the p-value also insignificant, right? So there is a no causal, no feedback relationship between these two variables. So this is a class activity for you to test for these three variables, for not only money, also income, interest rate, and the exchange rate as well. So the instruction is use a double log model and test the correlation with EG and JJ test with EUs. So the question asks, where is that interest rate Granger cause the money demand in the long run and the short run? So this is your exercise, right? Did I show you exercise? I also showed the answer already. Too nice, right? So it's okay. So again, first step, run the regression. And then this is Angel Granger, idea, same idea, or S with all my independent variable, and then get the ECT, then perform the Dickey-Fuller test for the Angel Granger. Alternatively, you can just first difference the ECT, same, right? ECT minus 1, and then regress on the constant term as well as the ECT t minus 1. Yeah, ECT 1 t minus 1. So same idea, or you just use the function UniRoot. Just use this function UniRoot button, right? And then just click on the ECT test for the stationary, not stationary. Same idea, but here you just based on the significance of the beta 1. Okay. So same idea. This one, right? Yeah. So bring back here. So it's greater than the what we say the Angel Granger critical value, right? So significant at 10%, so reject. So there is a correlating relationship. And then the error correction models, again, I want to test whether the DIR Granger cost the money or not, right? So I first difference my models, all my independent variable as well, and then my ECT minus 1 here. So ECT minus 1 significant, not significant? So significant, right? Significant, but not able to test the long run causal. Why? I just can say there's a long run causal, but cannot say long run causal for the interest rate to the money. Why? Because this ECT also consists of the income and exchange rate, not only interest rate, right? So I just can say that there is a long run causal. Or maybe I can say there is a long run relationship amongst the variable of interest, right? How about short run? Short run from the money, right? This refer to the money, right? How about the short run? This one, this one. Not significant, right? Not significant. P-value also not significant because P-value is lesser than the alpha value. It's not significant. Alpha value, maybe I can test 0.05, so lesser than 5%. Alpha value 0.05. So no short run. Only there's a long run causal, but not from the interest rate to the money. But we're not able to see, right? How about based on the WAR? Based on the WAR, selection. For the VCM, I have a 3, right? I have a 3 legs. I have a 3 legs here based on the AIC, but only I have a 1 leg based on the SC. So if you believe that, if you not say believe that, if you want to follow based on the AIC, then you run a model with the 3 legs. So if I say my sample size is very small, 739, then I use the SIC, then I just have a 1 leg. So leg 1 for my co-integration. So let's say I use 1 leg for my co-integration. So this is my result. Okay, this is my result. So I can know my income have a positive impact on my money, and then my and also as well as my interest rate have a negative impact on my money. But my exchange rate is insignificant given us the insignificant test statistic, even though the exchange rate has a positive impact on the money demand. Okay, so this is based on the long run relationship. Then how about the co-integration? The co-integration, this one significant, this is significant, this is also significant. There is a significance of the ECT in these 3 different models. Okay, then how about the trace and eigenvalue? For this trace and eigen, this is a classical example. This is a classical example to show you that these 2 test statistics provide you different results. Why? Why? Because this eigenvalue totally not significant, right? Totally lesser than the 5% critical value. But this trace statistic significant, right? At 5%. So we can say that there is a different result based on this trace statistic. So what I can say, I have a 2 co-integrating vectors, right? Yeah, I have 2 co-integrating vectors. I have a 2 co-integrating vectors in my case. Not only 1, 2. So how are you going to solve this case? You have to do the restriction, right? Do the restriction. There's I will show you the result. I will show you the journal how to people do the restriction based on the if we found out this is the case if we have a 2 co-integrating vectors. Okay. Good. I have 4 variables, right? 1, 2, 3, 4, right? So if I have a 3, I have a 4 co-integrating vectors, that's this full rank. That's the problems already. So 2 credit means I have a 2 endogenous equation. So based on the result, is it interest rate gradual cost the money? Have we answered the question? Interest rate cost the money. So I can base on this money, right? Money as my dependence. So interest rate actually insignificant. Interest not gradual cost the money. Okay. So 3 ways causality. So there is you can refer to my spectrum. I share you the links, right? Share you the URL, the links to see how people the 3 ways for the causality by using the emails. Okay, so 3 ways here. I think up to 101 minutes, right? For this 10 minutes video, so you can spend the time to go through it. So there are 3 different ways. One is based on the regression and ECT, how I show you just now. So actually, it's also talk about the strong causal. This one I like you to expose strong causal effect. What it means by strong causal? How to get the strong causal effect? Is there a strong causal? So that's just a key point for you, to the strong causal, and how you run the short run, and how you run this long run, and also the strong causal. So that is for your exercise to talk about the long causal in the videos that we not touch today, right? So by the way, let me show you how to perform the Johansson, right? Okay. Simple idea, right? Let me see. Okay, RM2. Now I will show you just now RM2 and GDP. I open them as a var, right? As a var. Then here I want to test for the how many legs, right, in my variables. So I just use as default one. I just click OK. So I go to the view here, then leg structure. Then I go to the leg structure here. I go to the leg length criteria. Leg length criteria, leg to include is 5. So here is the case. So just now I show you also, right? It's a 1 leg here. Okay, one leg. So once identified is 1 leg, then I go to the view here. Then I go to the estimate again. So I need to go to the vector error correction. Okay, vector error correction. There are so many other methods here. So Sichuan, mixed frequency, Bayesian one. So I use the vector error correction. So the lag for the lag here is 1, 1. Means that I include the one lag for my lag dependence, one lag for my dependent, as well as one lag for all my independent variables. So that is called lag length 1. So endogenous variables, also two variable case. Then exogenous is exogenous variables, which is not my interest today. So I just assume these are the two variables I'm going to handle today. I click OK. So this is the result I replicated just now. Okay. So I go to view here. I can go for my integration test. So once you click on integration test, you click OK. So actually this is a critical value from this Mackinnon's equals. Okay. And these actually have a different models. So we have a dual constant, we have unrestricted constant, and then we have integration constant. Actually, normally we run the case tree okay, unrestricted constant, for example. So actually it's a short run dynamic input a constant term, a constant variables. So against exogenous variable, I let it inside. Exogenous variables is actually outside the conjugated equation in the short run. For example, you can put in a dummy inside, but for the long run, it's inside the equation. So that is have to be quotient. Okay. Okay. So this is my result. Okay, this is my result. I do it just now. So I have a trace statistic as well as a maximum agent value. So okay, so this is my result. And this is my long run. My long run result, right? My long run result. So I can, what else I can get from my result I showed you just now? Yeah, Granger, right? Yes, Granger. So I also show you the Granger causality. So this is a Granger, how we get from the mean. If let's say there is no integration, right? Actually, we can just simply first difference a variable. Let's say I first difference a variable already. Then I open them first difference and first difference a series first. First difference a series first. Then open them as a group. Okay, also open as a group. Then go to the view there, and then go to this one, Granger causality. So and I like to be included is 1, right? I just now our case also 1. So I put in 1 there, then I click OK. So this is another type of this is called pairwise Granger causality. So this is pairwise Granger. This is like what we discussed last week. This is the different compared to the model we discussed just now. Also, there is a no feedback relationship between the M2 and the GDP. Okay, just like our case, actually it's just complement each others, right? This is pairwise, and then there's based on the vector form. Both also found that there's no Granger causality. Okay. Okay, I think okay, good for today's lectures. I stop sharing here. So so far so good, right? I think one student also dropped from my class already. Run away, right? So okay, it's for if I have any question, right, you can try to ask me once you go through the slide and then go through the video again. So if any question, you can ask me next week, physical. So okay, next week we're going to touch on the AIDL, autoregressive distributed models. We're going to emphasize again on the Granger causality and also the short run and also the strong causal. So I let you to go through the video I posted in the spectrum here, right? There is a several videos here, right? Yeah. Causality test with single equation, with the VCM, and then with SO, and also this VCM approach estimation. You can go through the slide, go through the video. Perhaps my interpretation also not that details, right? So because it's quite difficult to cover this big topic within 3 hours. Okay, so if you want to go through the original paper, you can refer to the Andrew Granger paper in 1987, and also the paper I shared with you 2003 and 2009 for the means that actually done by Biologic. Okay, so that's all only for my side. So any questions so far? So far so good, right? Yes.
We will digest and come back to you, Dr. Sun.
Digest, so you can digest and come back me next week also lah. Okay. Okay, you can go through the video, and then if you have any question, please jot down, and then you can direct me next week. Okay. So that's all only for my side. So have a nice dinner. So sorry for no break. Straight forward from the 6 to 8:25 already. So, okay. So see you all next week physical in the Magmao G2, G3. Okay. Okay. See you all.
Thank you,
Bye.
Dr. Sun.
Thank you. Bye.
Thank you, Doctor.
Thank you.